This man's discoveries scared Einstein himself. But you'll have never heard of him, because the maths you've been taught your entire life is boring. Schools don't teach the mind-bending stuff, because if they did, you'd start asking questions that they aren't built to answer. But to fully understand why, we need to unlearn everything they taught you. Let's solve this equation here. It looks relatively simple, doesn't it? But 44% of the general population can't do it, and the remaining 56% don't agree on what the correct answer is. And that is because the answer depends on the calculator you're using. I'm Lewis from Learnaholics, and I answer questions that nobody asked. Everyone remembers PEDMAS, or BIDMAS in my case, from high school. You start with parentheses, or brackets. After that, you do your indices, or your exponents, to which there are none here, obviously, and then you just do your multiplication and division from left to right. So the answer here is obviously 16. Right? But the catch is, you don't know if whoever wrote this equation meant to write it like this or like this. These are exactly the same equation, but the difference between them is one has one answer and the other has two. This is to do with implied multiplication, the maths rule that exists or doesn't exist, depending on the mathematician that you ask. Some people will argue that everything that surrounds brackets should be counted with the brackets. So if you're following PEDMAS and you're doing the parentheses or the brackets first, it's not just the 2 plus 2, it's the 2 times the 2 plus 2. And other people will argue that that is complete nonsense and just follow PEDMAS or BIDMAS like normal people. Some calculators account for implied mathematics, others don't. So this one equation has two answers, 16 and 1. But what this really shows is that despite popular belief, mathematics is not linear. There isn't always a definitively correct answer. And that's a problem for mathematicians. It challenges the most common and well-understood beliefs about mathematics. And it's the reason that teachers as a whole avoid this subject completely. The reason that people fall in love with maths, go on to study it, and in times dedicate their entire life to it, is because it provides certainty. Like many, I was a shy, socially awkward fat kid back in my younger days, and like everyone else back then, I was drowning in uncertainty. The pressure to pick the right subjects that I'm going to go on to study for possibly the next 10 years of my life. There's something that my teachers said to me years and years and years ago that has stuck with me genuinely up until this point in my life, and I don't think will ever not affect me. Whatever you choose, Lewis, I know you'll do great at. And of course, at first that sounds supportive, but it's haunted me. Because that choice, that one choice I made at 12 years old, has dictated my life up until this very point. And that choice, like many others made, was to cling to the safest and sturdiest thing that I could find. The reason and the logic. And that is mathematics. But as I got older, I realised that I made a huge and common mistake. I was drastically wrong about maths. There is a way of looking at maths that has been hidden from you for far too long. One that you actually find joy in understanding and exploring like its own adventure. And that version of maths is exactly what this incredibly smart man dedicated his entire life to discovering. This was the man that Einstein respected so much that he said, and I quote, "I came to the Institute merely to have the privilege of walking home with him." The creator of the incompleteness theorems, which we're going to touch on very quickly in a second. And of course, the creator of his own mathematically sound universe that tore a hole so big in maths that we are yet to patch it up. Of course, I am on about Kurt Gödel. His most famous work revolved around one statement, that not all truths can be proven. And the way that he went about this is so insanely clever. The whole thing is based around paradoxes, things that make no logical sense. For instance, if I was to say, this sentence is false. If the sentence itself is false, well then the sentence is true. But then if the sentence is true, it also has to be false. This is an example of a paradox, but it's a paradox that exists in language. So you might not think that these kind of loopholes could exist in the certainty of maths, yet you'd be incredibly wrong. Probably the most famous one was Russell's paradox. It's about sets of numbers. So imagine a set, for 1 second, like a club with a list of members. This is Club M, for example, and the members of this club are all of the multiples of 2. 2, 4, 6, 8, on to infinity. Maybe another club, Club L, can contain all of the prime numbers, so 2, 3, 5, 7, 11, all the way up until infinity. But Club X contains all of the members of Club M and Club L, because clubs or sets can contain other sets. But there's one more thing you need to get your head around as well. Let's imagine another set, and we'll call this set lambda. This set contains every other set. So not just M and L, but also A, B, C, set S, O. It doesn't matter, it's an infinite amount. This set also contains itself, because of course it itself is a set. Sets can contain themselves. And now this leads us on to Russell's paradox. This is set R. And the definition of set R is it contains all other sets that don't contain themselves. So the question arises, and what Russell's paradox is does set R contain itself? Well, let's think about this logically for a second. Let's say, for example, that set R does contain itself. Well, if that was the case, then it shouldn't contain itself. So we'll take it out again, because obviously the set contains sets that doesn't contain itself. But then the set doesn't contain itself. So it should, in theory, contain itself. And of course, then we find ourselves in the same situation as this sentence is false. When this paradox was first published, mathematicians coined a new term: depression. Granted, it wasn't the first paradox ever to be discovered in maths, but it was one of the most important. And that's because it was the most publicised. Suddenly, the entire world knew that this basic, rock-solid foundation that maths is, this beacon of certainty, contained something that completely defied logic. Something that it cannot prove and never will. And that is because it physically can't. As a young mathematician in his 20s, Kurt Gödel was obsessed with proving things. However, just like everyone else in his generation, he couldn't quite find a way to disprove these paradoxes. So of course he took the next logical step. He decided to prove that paradoxes couldn't be proved. This man used maths to create a language that maths itself could use in order to explain itself. And that might take a little second to sink in, because it's fucking ridiculous. The overview of what he did was he managed to convert every known and possible formula into its own individual number, a unique fingerprint, you could say. Then now, because formulas are numbers, he could use basic arithmetic to do calculations with formulas. But how did he know what numbers to assign to each formula? Because assigning 1 to each individual formula by hand would have taken him years. And how did he actually use these numbers to create an entire language inside of maths? Seriously complex maths. And that's why I'm not going to go over it in incredible detail here, because it would take up about 2 hours of your life. But I believe it is super interesting. So if you are interested in going a bit deeper into that, I'm going to go over it on my newsletter for the next 2 weeks or so, just to split it up and make sure we truly get it. But the point now stands that maths will always be incomplete. And that alone should shake your confidence in the idea that maths equals truth. But of course, Gödel wasn't done there. He wanted to prove that even the things that we have proved don't make any logical sense. And so he went on to prove that time travel is possible. Oh, and of course that time itself isn't real. And he succeeded, by the way. In 1949, yes, you heard me correctly there, 1949, Gödel proposed a solution to Einstein's field equations of general relativity. He proposed his own mathematically sound universe that later became known infamously as Gödel's universe. A bit of backstory first though, because Einstein and Gödel were colleagues at the Institute of Advanced Study in Princeton from 1940 to 1955 when Einstein eventually died. But even though they were in separate faculties completely, they were extremely close friends. They bonded over their shared skepticism about time. And as Gödel was pulled into the world of physics by Einstein, they came up with a very common theory together that I'm sure you've heard before. Gödel had studied physics before, but at this point it was long in the past, so he was coming in with a fresh set of eyes and a unique starting point. A starting point that allowed him to ask questions that Einstein hadn't even considered, to see the equations in a whole new light. And in doing so, he found a solution that wasn't very practical, but it worked. And it worked too well, to the point where Einstein was quoted saying that his findings were extremely disturbing. Gödel's universe, which I will admit looks a bit strange, but let me explain what all of this means. I'm going to presume here that you're familiar with Einstein's definition of space-time, but I'll do a very quick example if you're not. In short, what it is that space and time is curved by mass and energy. Imagine this sheet of fabric here like space-time. Right now, it's completely flat, and that's because there's no mass or energy on display. If something was to move through space-time like this, it would be in a completely straight line, because this plane is not curved in any way. But as soon as you introduce some mass, you'll find that the fabric itself curves. The fabric of space-time. So now when something moves through space-time, it's going to follow these curves. And that is what Einstein described as gravity, and why things orbit other things. It's not that something is getting pulled towards a planet, it's that space and time itself has been warped, and therefore the path that the object follows is different to if there would have been no planet. The red lines that you see on this diagram are the paths that objects take through this space-time. As I'm sure you've seen, these lines curve, so you probably are screaming at the screen, where's the mass? Where's the energy that has forced these lines to curve? Well, the thing is, the contents of Gödel's universe is actually just spinning dust particles. It's quite uniform. There's not really any localized mass or energy, not big enough to cause those lines to curve anyway. So what's the reason for it? Gödel's universe is rotating, kind of like this cube, but also not like this cube. You see how these 2 points that I'm connected to here, the top and the bottom, they don't move when I'm rotating it nearly as much as the outside points. And that's because this cube is rotating around a fixed point. Gödel's universe doesn't rotate about a fixed point. It rotates like a screw. It rotates around its center and it moves through space. You see this spiral that's on the screw? Does that look familiar? This distortion is what's physically bending space-time itself. It completely bypasses the need for mass. What I'm also sure that you've noticed is that these lines all converge on points that we call equators. And because they converge, you'll notice that they create loops. These lines are paths objects take through space-time. So if they loop, then the maths is quite literally proving that closed time loops exist. You've definitely heard of these before. Exhibit A, you go back in time to talk to your younger self, give him some advice on the future, and then pop back to normal time, go on about your day. Your younger self, in a different time, then grows up to be the same age you were when you went back in time, and suddenly realizes, oh, it was me who came back in time all those years ago to give me that advice. And so he does the same, and then the person he did it to does it as well, and yada yada yada, the time loop is closed. This goes on and reality is completely uninterrupted. But what if you were to go back in time and kill your grandfather? Well then, you wouldn't have been born in that time, and you wouldn't have been able to grow up and go back in time to kill your grandfather. What would happen in this scenario? Well, I don't know, and neither did Gödel. All that this means is that it's possible. And in theory, if you were to stick around long enough in Gödel's universe, you would be standing in the delivery room watching yourself be born over and over and over again. One of the biggest issues we have with this universe is that it's a clear breach of causality, and that's the relationship between cause and effect. Obviously, if you have a gun and you want to shoot someone, that person won't die until you pull the trigger. The cause has to come before the effect. However, in this universe, at these equators, at certain points in space-time, causality completely breaks down. And at that point, we genuinely have no clue what it would look like, because it's incomprehensible. But even though it's unfathomable, it's been proven true. And this is, in essence, the complete opposite of the incompleteness theorems. The theorems state that there are things that are true that can't be proven true. Whereas Gödel's universe says we can prove this is true, but clearly it isn't. But the most mind-blowing conclusion that we can draw from Gödel's universe is this. If time loops and causality breaks down in the way that it would, then time doesn't really have any structure. The present, the past, and the future that we describe as a linear thing that we experience blurs into one. The present moment that we see as quite literally an absolute moment is actually just a perspective our brain has created that's trying to comprehend this massively complex and looping structure that is time. Because in this universe, time itself is an illusion. But don't worry, because our world isn't broken just yet anyways. Even though Gödel's math works perfectly, most people don't actually believe that we're living in said universe, even though they can't prove it for sure. As I've already said, Einstein himself, who, by the way, got this paper as a 70th birthday present from Gödel, what a little prankster, said that it was disturbing, but also that he couldn't prove it wrong, so he had to take it seriously. As well as this, we are also fully aware that the universe we live in is expanding, and it's expanding at an accelerated rate. It's increasing in speed over time. Gödel's universe describes a static universe, one that isn't growing, one that isn't shrinking, all it's doing is rotating. Although we've proved it fact, it doesn't make it true. And by the way, that is another paradox. In essence, what we've proved here is that maths itself kind of has to be wrong. And if you're still not convinced in the idea that maths isn't complete certainty, I've got one more thing for you. This is arguably the most famous crossword puzzle of all time. The New York Times released in 1996, the day before the US election between Clinton and Bob Dole. Everything was going completely fine for the people doing the crossword until they got to the clue for 39 across, which read the lead story in tomorrow's newspaper. And the answer was blank elected. So the question here is, how on earth are you supposed to get the right answer when you seemingly have to be able to tell the future in order to get it? Well, as it turns out, the correct answer was Clinton elected. Or Bob Dole elected. Both answers fit perfectly into the crossword, completing every other word just in two separate ways. Whoever designed it was absolutely genius. There was two truths that fit the one question. And basically what I'm trying to get across here is that just because one thing works doesn't make it the only, or in cases, the best way to go about something. Just because our current model of maths works for the majority of things doesn't mean there's not another one that works just as well, if not better. Even if we think something is impossible, we should accept the fact that we as humans don't know everything. And we should just try something anyway for the sake of asking the question. So now the final question that remains is, why am I still in love with maths? Because one, I'm not 12 anymore, And 2, the certainty that I thought was there has just been thrown out of the window. I've been hunting for the answers for this certainty the entire time I've been going through maths. But the thing is, I enjoyed it before I got to the answer. And that kind of made me realise that the joy never came from the answers. It came from asking better questions. The ones that make your brain physically lag the first time you hear them. The ones that don't fit into a neat little answer box. The ones that don't even come with answers at all. The ones that most people, probably yourself included, are afraid to answer. And to be honest, I completely understand. But that's what I've started Learnaholics for. To teach people that there's an immense amount of joy, amount of fulfillment in asking questions, in being curious, because nothing ever started with an answer. And anything that did start with an answer is a complete load of bollocks. Everything starts with a question. And if you ask the right ones, then you're not going to get bored or scared trying to find the answers to them. I have the tools to learn. I've been doing it for years and I am quite good at it without patting myself on the shoulder too hard. So I want to learn with you. And if that sounds interesting, I'll link it down below. But if not, then watch this video instead, because in essence, it's doing the same thing. It's scratching that itch in your brain. Either way, thanks for watching.